Well, as we head into the new semester, we're going to go right into chapter 14, looking at chemical kinetics and what that plays into the relationship of a reaction and how it might occur. Okay, so kinetics is the study of the rate at which a chemical process occurs. So, um, what causes or what are the components that lead to how the reaction actually occurs is really what kinetics will kind of allows us to figure out. So obviously, well, maybe not obviously, but kinetics at one reveals like the speed of reaction, whether a reaction is slow or fast, but also maybe how the reaction actually occurs on the atomic or the molecular level. Like how do atoms come together? How are they breaking apart? Because some of the kinetics can kind of, I don't know, explain or lead us to have a better picture of what might be occurring when the molecules or when bonds are being broken and new bonds are uh, forming. So what are some of the factors that affect reaction rates? One factor that affects reaction rates is the physical state of the reactions. So for molecules to come together, they have to come in contact. So, you know, if the states are solids versus liquids, fine powders versus big, you know, just large solids, gaseous versus not or solution. So we'll look at some of those different states and whether or not it's a homogeneous mixture of reactants or a heterogeneous. Um, so if, yeah. So here, an example being also another factor that affects reaction rates would be concentration. And concentration is that idea of if you have more reactants that are able to combine, then you're going to get a faster or greater reaction. So the picture here is of steel wool being burned. So the first one is being burned in over a flame to atmospheric oxygen, so it burns at some rate. And then the second one is a picture of steel wool or really hot wool being placed in a Erlenmeyer flask that's filled with pure oxygen. And in that case, there's a lot more oxygen present, so therefore the reaction can occur faster. More molecules can combine to make the reaction occur. And as we've seen in other portions of chemistry, increasing the temperature creates more kinetic energy for the molecule, so everything's going to be moving faster. And if you move faster, you can there's more collisions, and with more collisions, there's also greater energy associated with this collision. So you're going to get more more reactions through that process. And then the last component that would affect reaction rates would be the presence of catalysts. Whether you have something, so a catalyst is something that speeds up the mechanism or changes the mechanism of the reaction so that the reaction occurs faster. Your body utilizes lots of catalysts in the form of enzymes to make reactions go faster, because without them, the reactions really wouldn't occur at the temperature that your body is. You would have to burn a lot hotter, which is not safe for life. So yeah, so those are our components. And the nice thing about catalysts, both in industrial chemistry as well as you know, body or living chemistry, is that the catalyst itself is not consumed. It's just present and facilitates the reaction to go faster. So let's get into section 2. So that was 14.1. Now 14.2 is looking at reaction rates. So when we calculate rates of reaction, it's basically determined by monitoring the change in concentrations. So when you start, you know, you have, so we've got these jars here, and this is also found on page 575 of your textbook, but you start out with 1 mole of substance A, and you have 0 of substance B, and over time you see a change in the amount of both materials, and so you would measure, basically determine the rate of change occurring. So here we have an example of, so this is what, butyl chloride, and it's combining with water to make probably butyl butyl hydroxide, or yeah, butyl alcohol, and hydrochloric acid. Okay, so over time, you have all butyl chloride, okay? But over time, measured in 50-second increments, the quantity or the amount of the butyl chloride slowly goes away. So the rate of reaction can be measured by this part. Oops, sorry, I'm going to move this a little bit. By this lower part here, the average rate is equal to the change in the concentration. The brackets around the butyl chloride stands for concentration. So the change of concentration over the change in time. So you notice how we have broken it down for every 50 seconds and looked at the average rate for those 50-second increments. And obviously, at the beginning, the rate is much greater versus at the end, when we're at, 300 seconds difference, and the rate's just slower. It's just a slower reaction as we get further. Now, why might that be? Why might the average rate decrease as the reaction proceeds? What would be hindering the reaction from continuing at the same rate the whole time? Well, if you think about that for a moment, you might consider the fact that as you go along, there's fewer and fewer particles around, or reactants that haven't reacted yet, and those reactants have to find each other and collide with each other to make a product. And so as the reaction continues, you get fewer of the proper collisions, and so the rate is going to slow down over time. So if we plotted this data over time, we would see kind of this decay curve. And if we wanted to know like the rate of the reaction, we typically are going to refer to the initial rate. What is the rate if we measured it right at time equals 0? How does it change just at the very beginning of the graph? Because as you get to the lower part of the graph, it's less of a reflection on really the speed or how quickly this reaction goes. So the slope of a line tangent to the curve at any point is the instantaneous rate at that time. And if you are taking calculus, you could think about how you might find the instantaneous rate doing some calculus. Obviously, we are not going to focus on that component, but it is one way that you could explore deeper the reaction rates of chemistry. So the best indicator of the rate of reaction is the instantaneous rate near the beginning of the reaction, because that's really how it's behaving right at that beginning moment when you combine the two starting materials. So in this reaction, the ratio of butyl chloride to butyl alcohol is 1:1. So from one starting material to one ending material. So it's a 1:1 ratio in this balance equation. So stoichiometry-wise, it's fairly simple. So the rate of disappearance of one is the same as the rate of appearance of the other. So they are equal in that sense. And note for this rate reaction on the bottom, there's a negative sign for the reactants, and well, obviously a positive sign for the products, because we're producing more of those over time. Now, what if the ratio is not 1:1? Let's say we had this hydrogen iodide, and it decomposed to produce hydrogen gas and iodine gas. Well, in this case, the rate would be -1/2 to the change in the concentration of HI over delta T is equal to the concentration of I2 over delta T. And so if we wanted to generalize this, just to kind of think through, so if you have a reaction A plus B produces C plus D, with the lowercase a's, all the lowercase letters indicating the coefficients that might be in front of those compounds, then we could rewrite the rate equation to be this way. So all the reactant rate components would have a negative sign with them, and all of the product ones would have a positive, and you'd have this relationship with their coefficients as well. And that's where we're going to stop for today as we head into kinetics. And we do not have a lab on Tuesday, so plan accordingly. And I would like to collect your lab books if I didn't get them on Friday. I would like to get them tomorrow in class.